Hello, everyone. I welcome you all to the Placental Vessel Segmentation and Registration in Fetoscopy Challenge presentation. This challenge is organized as part of the MICCAI-Endoscopic Vision challenges. Let me introduce you to the FetReg Organizing Committee. I am Sophia Bano, and with me the co-organizers are Alessandro Garcia, Francisco Vasconcelos, Sara Muccia, and Daniel Slono. We are all part of one or more institutions listed in this slide. We are very excited to have the support from three major fetal medicine units from across Europe and also from the Gift Search project. And also, we are extremely thankful to our sponsors, Medtronic, NVIDIA, and E4 Computer Engineering, who supported this challenge. So let's move on to the clinical context of this challenge. Fetoscopy laser photocoagulation is a procedure which is used for the treatment of twin-to-twin transfusion syndrome. TTTS is a fetal anomaly that affects identical twins sharing a monoclonic placenta, where in TTTS, the flow of blood between the two fetuses becomes uneven. As a result, the donor experiences slow growth while the recipient is at a risk of heart failure. So in order to treat this, fetoscopic laser photocoagulation is performed, in which the surgeon inserts the endoscope or fetoscope into the amniotic sac and localizes the interfetus membrane and use it as a guide for finding the abnormal connections. Once these abnormal connections are localized by the surgeon, these are then ablated with the help of a laser tool, and in order to disconnect the flow of blood or regulate the flow of blood between the two fetuses. This is a highly challenging procedure because the field of view is very limited in this procedure. Moreover, the visual conditions are very difficult and they vary a lot from one patient to another patient, as you can see in these three examples. There are conditions such as poor visibility, low resolution, varying illumination, fluid turbidity, and also specular highlights and occlusion occurring in a fetoscopic scene all the time. And if I talk about challenges from creating or increasing the field of view of fetoscopy, these views are highly dynamic. And also because this procedure is performed using a monocular camera, the ground truth transformations or registrations are not available for mosaicing. Nevertheless, we believe that computer-assisted techniques can improve this procedure and can guide the surgeons during this procedure to improve the surgical outcome. Therefore, we started looking into the task of fetoscopy registration. One of the major challenges in fetoscopy data is the interpatient and intrapatient variability. Moreover, fetoscopy videos captured at different clinical sites varies also in terms of the recording setup. Therefore, we started collecting large-scale multi-center fetoscope data from three major sites across Europe. These are University College London Hospital, Tenena Slini Institution in Italy, and University Hospital Leuven in Belgium. Using this data, we come up with two tasks for this challenge, where the main aim was to design generalized algorithm for solving these two tasks. These two tasks are, number one, the placental semantic segmentation, where we label the data for three classes, which are vessel, laser tool, and fetus presence. The second task was placental RGB frame registration for mosaicing, where a demo is shown over here, where the task was to compute the transformation or homographic transformation between adjacent frames and to create a mosaic from these transformations. The collected data set was then annotated to obtain the ground truth for the segmentation task. We were given guidelines from the clinician on the three labels that we wanted to annotate on each frame. The annotators followed these guidelines and annotated the data set. Then this data set was reviewed by 2 researchers, and if there was a need of improvement, this was flagged. And if there were some frames which were difficult or which were ambiguous to annotate, we went back to our clinicians to verify our annotations. For the evaluation of segmentation tasks, since the ground truth was available, we can directly compare the predicted labels with the ground truth labels to evaluate or to quantitatively evaluate the performance of the segmentation model. We use a mean intersection over union as a measure over all test data for this purpose. But in terms of registration, since no ground truth is available because these videos are recorded in vivo setting and from a monocular camera, we looked into evaluating the consistency of the registration overlap. We used the metric that we presented in our last year's MICCAI paper for the purpose of quantitatively evaluating the registration. The registration evaluation is based on the assumption that adjacent frames will still have overlaps within a window of n consecutive frames. So let me quickly go through this registration evaluation process. So given the test clip, which is of n frames duration, the submitted registration algorithm computes the homography between the adjacent frames, which are represented over here. Then using these homography, we wrap frame 0 onto frame n, and then compute the overlap between these 2 frames. And then in the overlapping region, we compute the structure similarity index. The mean and median over the structure similarity index is then used as the evaluation metric. Now let's go through the training data set that we released. For the segmentation task, we released 2,060 images with pixel-wise annotations from 18 fetoscopic videos. These images were labeled for vessel, laser tool, and fetus classes. Here you can see the bar plot showing the occurrences of each class per frame, and also the average number of pixels present per class per frame. From these plots, what we can observe is that there is the data set is highly imbalanced in terms of the 3 classes that we are interested in. For the task of registration, again, we released short video clips from these 18 fetoscopy videos. In total, we released about more than 7,000 frames, but then these frames were not annotated for vessels, or they did not have any ground truth available for the registration task. In terms of the testing data set, this data set was not released to the participants, but it contains 6 in vivo fetoscopy videos, about 658 images with pixel-wise annotations. Again, we see the same trend of class imbalance in this data set as well. And talking about the data set for the registration task, it contains 6 short clips from the same videos and more than 2,000 frames, unannotated frames. The evaluation for the registration task was performed on a subsequence of 200 frames from each video clip, such that this subsequence was free of occlusions, or the views in the subsequence was relatively planar or had some vessels clearly visible.